Good day everyone, and welcome to the second video in a series of videos narrating or giving a storytelling for the discontinuity of a piecewise function on an interval. In the first video, we completed the table of x and y values to ensure that all of the elements of the interval produce a y value, which is an element of the real number system. Alright, so here for step number 2, we're going to check the behavior at internal boundaries. So we're going to check if the limit is continuous and thus exists at the boundaries. We will check the behavior of both the left hand and the right hand boundaries of the interval. So how? We are simply going to check whether or not the limit of the function as x approaches the left boundary, we denote it as a, exists and is equal to f of a. So we're going to check whether or not the limit of the function as x approaches the right boundary b exists and is equal to f of b. So please observe, we're going to evaluate the f of a by the process of substitution. For the left-hand behavior, we denote the left boundary as a. So a is equal to negative 2. So we're gonna do direct substitution, right? So negative 2 is less than 1. So the expression to use is for negative x squared. So here's the substitution. So the value of f of a is 0. After evaluating f of a, let's evaluate the limit by checking whether the left-hand limit and the right-hand limit of the function f of x exist as x approaches the left or lower boundary negative 2. We're going to compute the limit of the function, the piecewise function, as x approaches the left boundary a, that's negative 2, at the left side, or less than negative 2 and very close to negative 2. You can do this by creating a table of x and y values or by simply computing f of a using a value of a that are very close to the boundary a. So our boundary a is negative 2. So we can have an x equals to negative 2.00001. Right? So that's very close to negative 2 but not really equal to negative 2. So let's have x equal to negative 2.00001 and we do direct substitution, and the value of f of x is 0.0004001. So that is pretty much very close to 0, right? So we can see that the left-hand limit is approaching to 0. Not touching 0, of course. So, reminder, when performing the limit operation and the answer, for example, is 0, it means that as the x value approaches a certain boundary like a of negative 2, then the y value approaches 0 and not touching 0. So, GeoGebra time. So we are going to input x values that are very close to negative 2 and at the left of negative 2, meaning less than negative 2. So we have the x values negative 2.0001 and then this is the y value. Then we can have an x value of negative 2. This many zeros and 1, that is our y value, and another x value that is more closer, or that is very very close to negative 2 at the left, meaning less than negative 2. Then eventually GeoGebra will give an answer of 0. Here in GeoGebra, we are going to type the function, and the function for x values less than 1 will be 4 minus x squared, right? We're gonna do approximation. We're going to input x values that are very close to negative 2 at the left, meaning less than negative 2. smaller than negative 2. So please observe, so we are going to have our first value, x value, that is very close to negative 2 at the left, meaning less than negative 2. So we have this one, negative 2.00001, and we have the y value here. Okay, and then another x value, x value less than negative 2 and very close to it, and this is the y value. Okay, so you continue the process, then eventually GeoGebra will showcase that the limit of the function for minus x squared as x approaches negative 2 at the left side will be equal to 0. So please observe, we will do the same drill for the right-hand limit of f of x as x approaches the left boundary from the right. And yes, the right-hand limit of f of x as x approaches a from the right, or the above limit, then the y value approaches 0 as well. Alright, so please observe. So our left boundary is negative 2. Okay, so we're going to compute, or we're going to evaluate the limit of the function as x approaches negative 2 at the right side, or greater than negative 2, but very close to negative 2. So we have the value negative 1.9999, for example. And then again, this is less than 1, x less than 1, then the expression to use is for negative x squared. Right? And then do direct substitution. Then we have this value, or y value that is very close to 0. Okay, then do the same in GeoGebra. We can then say that the left-hand limit and the right-hand limit are equal to 0, right? So the limit exists, and it's equal to f of a, or f of negative 2, which is also 0. Therefore, f of x is continuous from the left. Now let's check the right-hand behavior at b equal to 5. So 5 is greater than 1, so the expression to use is square root of x minus 1. So please observe the substitution process and do the same at your desk. Now after evaluating f of b, let's evaluate the limit by checking whether the left-hand limit and the right-hand limit of the function f of x exists as x approaches the right or upper boundary 5. We can do this by creating a table of x and y values, or simply computing f of b using the values of b that are very close to the boundary 5 as x values for a very small approximation. So please observe the manual substitution. Okay, so again, 5 is greater than 1. So we're going to use the expression square root of x negative 1. So the limit of square root x negative 1 as x approaches 5 at the left, meaning less than 5. So we can have an x value of 4.9999. Alright, so this is direct substitution. Alright, so the y value at x is equal to 4.9999 is 1.9999975. So it is very, very close to 2, or it's approaching 2. You can try doing the approximation in GeoGebra. So just input x values less than 5 and very close to 5. Okay, and then observe that the y values will be approaching 2 as x approaches 5 from the left, or less than 5. So as we can see, the left-hand limit is approaching 2, but not touching 2, of course. Again, here's a reminder. When performing the limit operation and the answer is 2, it means that when the x value approaches the right boundary b, which is 5, for example, the y value approaches 2 and not touching 2. So please observe, we will do the same drill for the right-hand limit of f of x as x approaches the right boundary b, which is 5. Alright, so we can see here that the limit of f of x, that is square root of x minus 1 as x approaches 5 from the right is also approaching 2, but not touching 2. Alright, so here's a friendly note. So for a piecewise function, to determine whether a limit exists by inspection, so please prepare and check whether or not we're going to use the same expression when calculating the left-hand limit and the right-hand limit. We can then say that the left-hand limit and the right-hand limit are equal to 2, so the limit exists and is equal to f of b, which is 2. Therefore, f of x is continuous from the right. Okay, so how do we display the x value where there is discontinuity? So by inspection, at which x value do we observe a gap? Okay, you have the gap here at the green vertical line, right? Yes, it's at x equal to 1. So we're just going to type x equal to 1. So we are just going to type x equal to 1. And then we can change the color. Okay, we can have a green, solid green. Okay, so at x equal to 1, then we have the discontinuity. So let's illustrate this discontinuity using the fundamental calculus theorem called the intermediate value theorem. Right, so if a function f is continuous on closed and bounded interval a, b, where f of a is not equal to f of b, then for any number k between f of a and f of b, there exists at least one number c that is element of the interval a, b, such that f of c is equal to k. Alright, at this second video, we have checked the behavior of the function at the intervals, and we have concluded that it is continuous at the left boundary -2 and at the right boundary 5. Right, so please do watch the third video. We are going to make use of IVT to prove that at x equal to 1 there is discontinuity. Okay, that makes the piecewise function discontinuous. So thank you so much for watching, and I hope that you have learned something.